Today we'll start with this new subject, right? As we have discussed yesterday or last time. Here we will start with machine design, and if you see the syllabus of machine design, then it is given like this in your that GATE syllabus. That design for static and dynamic loading, then failure theories, then fatigue strength and the SN diagram, then principles of the design of machine elements such as bolted, riveted and welded joints, right? Then shafts, gears, rolling and sliding contact bearings, brakes and clutches and springs, right? So basically these are all machine elements, so design of all these machine elements, and apart from that design for static and dynamic loading, right? So this is how we will see next, right? Previously we have seen that theory of machines. Now for this particular subject you can refer to NPTEL video course on this design of machine elements 1 by Professor Professor Chakrabarti and Professor Roy Chaudhary, right? So they are from IIT Kharagpur, and in case of reference book you can go for this design of machine elements by V.B. Bhandari, and you can go for this Shigley's mechanical engineering design, right? So today we will start with this design against this static load, right? So design against static load. So if we start discussing this, then the very first thing is what is this static load, right? So generally whenever one second. Generally whenever load is applied gradually, right? So this gradually applied load, right, on your any of the machine elements, and it is not going to change in its magnitude and direction, so it does not change in its magnitude and direction, then it can be termed as static load, right? So this is how you can define the static load. Yeah. So whenever we start discussing about this designing, so designing always includes this modes of failure. It means you are going to design component based on what we can say particular basically you are going to design component based on various types of stresses or forces acting on it, and based on that you will define certain dimensions of your component. So whenever you design, you have to design for failure also. Means whenever you are designing any product, you need to define which particular component of that particular what we can say system or whatever device you are designing is going to fail, right? So if we discuss about this modes of failure, then before even discussing about this modes of failure, you need to have idea about this tensile and brittle material. So what do we mean by this tensile and brittle material is actually whenever you are having this stress strain curve, right? So in that let us say this mild steel, right? So whatever this percentage elongation is there before failure, right, or fracture, right? Let us say this is a failure point or fracture point, right? So this particular delta is known as percentage elongation, Right, so how we are differentiating this tensile and brittle material is, if there is a material which is having less than 5% of uh, percentage elongation, right, then it can be termed as brittle material, and if it is greater than 5%, then it can be termed as that actually not tensile, sorry, ductile and brittle material, sorry. So if it is having greater than that 5% of elongation, then it can be termed as ductile material, right? So once you have idea about this different nature of this material, it may be ductile or brittle. So in case of now modes of failure, there are three different modes of failure, right? So first is it the your component may fail by elastic deflection, right? It may be elastic deflection. See, failure means what? Actually, whenever your designed component is failed to perform the intended task, right? So this is particular thing you have to mention for defining failure. So whenever any design component is failed to perform the intended task, then you can consider it as failure. So for some of the components like shaft or transmission shaft, if it will have that elastic deflection, then it will not be able to transmit the power for which it is designed, right? Similarly, failure may be due to general yielding. Now yielding means what? So once you are crossing this particular yield stress, right, or yield strength, right? So once the this yield strength is crossed, then this plastic deformation start, right? This plastic deformation starts. So sometimes whatever component you have designed, if it is going to be plastically deformed, then also it is not going to be able to perform its intended task, and that is why it is known as failed component, right? So failure by general yielding is also one of the mode of failure, and finally failure by fracture. So fracture means it will means it will be divided in two or many of the what we can say parts of a single component, right? Now fracture
So
generally
can you say till the elast proportional limit, beyond the proportional limit, it is started yielding.
sorry,
So if beyond the proportional limit, is it a failure due to yielding?
beyond proportional limit is failure. That is what you are asking, huh?
Yeah.
Yeah. So that is why, see, in case of any ductile material which is going to undergo that plastic deformation, if it go past by that what we can say proportional limit, or we can say that yield strength, then it will start plastically deforming, right? So in case of ductile material, if this plastic deformation remains, then the what we can say dimension of that particular component will change, and due to this changed dimension, the designed component may not be able to perform its intended task. In that case, it is going to be considered as a failure. Did you get it?
Okay, so uh, don't need to take it up to the yield point before it can be considered as failure.
See, means if the permanent deformation will remain, in that case we can consider it as failure, right? Otherwise, if that deformation is not taking place, then we cannot consider it as failure, because without deformation it may be able to perform its intended task. Okay.
Okay, sir.
So in ductile material this general yielding will be there, and in this brittle material, in this
Sir, if it is elastic deflection, like do we consider it as failure because the shape will be regained, right?
shape will be regained, but in that case during that particular time also, the whatever what we can say, design transmission ratio of the shaft, means on different shaft you may have this gears mounted, right? Let us say this is a shaft, and here also you will have another shaft, right? On both the shaft you have mounted this gear and pinion, let us say, right? So now a little bit of plastic, or sorry, not plastic, elastic deformation also may not be able to perform its intended task, and that is why it is going to be considered as a failure. Are you getting what I am trying to say?
Yes, sir. Like here, failure means not exactly breaking, right?
Yeah. Failure is not only meaning of this fracture. Failure has different meaning with different materials and different what we can say applications. So is it clear?
Yes.
Okay. So now once this modes of failure and this types of material is clear, then we can go for this factor of safety. So factor of safety is actually uh, given by this failure stress upon allowable stress. Right. 1 second. If somebody was there, I need to check. Yeah. Okay. Yeah. So, or in other words, you can also write it as failure load. Failure load upon this working load. Right. Now, why this factor of safety is required? Because in designing any component, what happens is there is uncertainty in the magnitude of force which is acting on the designed component. There may be variation in the property of material. It may not be same throughout, and there may be variation in the dimensions. It may not be exact with what dimension it needs to be manufactured. So, because of all these things, we need to consider some factor of safety, right? And magnitude of this factor of safety is going to depends on some of the factors like effect of failure. If effect of failure is going to result in some major accidents and all, in those application like in pressure vessel and all, in those cases this factor of safety must be high, right? Then it also depends on the type of load, whether it is gradually applied load or impact load. Similarly, it may also depend on this what we can say material, right? Similarly, the reliability with which you are designing your component, right? The cost or your budget, because factor of safety, if you are going to increase the factor of safety, the material requirement will be high, right? So this way there are various factors which are going to affect the magnitude of this uh, factor of safety, right? So once you have idea about this, then we can move to the next thing, I guess, and that is the stress strain relationship, right? So here I guess all of you must be knowing that this tensile stress and compressive stress, right? But before that, if we want to define stress, then can anyone what we can say, have idea about stress? Hello.
Sir,
So can anyone define stress?
Resistance
resistance
of the force per unit area. is
Hmm.
voltage.
So basically, yeah, thank you. So basically, whenever a mechanical component is subjected to some external force, as it is mentioned here, what is going to happen is a resisting force is going to set up, right? A resisting force is going to set up inside the component, as you can see, right? So this is external load applied. So stress is what actually, whenever a mechanical component is subjected to any external force, a resisting force is going to set up inside the material. So the stress is this internal resisting force divided by this unit area, that is known as the stress, right? It may be tensile or compressive. Similarly, so this stress you can define by this load upon area. Similarly, strain is this deformation per unit length. So you can define this strain as a deformation or deflection per unit length. Now, as we all know, according to this Hooke's law, yeah,
Sorry for interrupting, sir.
yeah,
One person would like to join into that session.
one second, one second. Okay, okay. So now this Hooke's law is, as we have mentioned here, this stress is proportional to the strain, right? And this proportionality constant is nothing but Young's modulus, right? So this is how you are having this sigma t is equal to this Young's modulus into strain, right? So if you put all the values, right, then what you are going to get is their deflection, right, in terms of this what we can say, this load per unit area and then length. So in that terms you are going to get your this what we can say, this deflection, right? So let us write actually all the values in this equation itself, right? So if you write sigma t, we want to find this delta, right, in terms of this force, area and total length. And also if we write this stress as P by E, and E will be as it is, and this strain will be delta by L. So from this you will be able to calculate your delta as PL upon AE. Right, so this is how we are having deflection. Now there are certain assumptions made whenever this calculations are being done, like material is homogeneous, right? Then gradual load is applied, right? And this actually this stress strain curve and all for a material will be calculated from a tensile test. So tensile test they are performing on some particular tensile specimen like this. There is a standard, right, of preparing this tensile specimen. So they are going to prepare this kind of tensile specimen. In that tensile specimen there must be some gauge length, right? This gauge length will be there in that tensile specimen, and it will be loaded on uniaxial tensile machine. So it means there may be one end fixed, right, and the other end the load will be applied. So only uniaxial load will be applied, right? So it is uniaxial tensile machine, so it is known as that UTM setup, right? So what is going to happen is one extensometer will be there in this gauge length. Extensometer is going to measure the deflection, right? So what is going to happen through this test is you are going to get a data of load per deflection. Here you will have load, here you will have deflection. So this load per deflection will be given by this extensometer. It is kind of strain gauge, right? So you will get this load versus deflection data from this tension test, and this load versus deflection will be then converted to that stress strain curve, right? So while having this a stress strain curve, what assumptions we are making, that is what I am telling, like homogeneous material, then load is gradually applied, then the force is acting through the geometric axis of the cross section, right, and there is no stress concentration is considered. So these are some of the assumptions while we are discussing about this stress strain relationship, right? So once you know about this stress strain relationship, then you can have idea about this shear stress and shear strain. So this is also type of stress which can occur in some specific applications, right? Like in Revit you may find this kind of stress is acting. So basically shear stress is what, whenever any external force is trying to slide the adjacent planes with respect to each other, right? Then resulting stresses are known as this shear stress. So this shear stress is given by this tau is equal to hello. Hello, can you hear me?
Yes, sir.
So
Yeah, now you are
yeah,
audible.
yeah. Sorry for some interruptions, right? So yes, this tau is equal to P by A, right? So here, as you know, this is the area on which this stress is acting, right? So this is how you are having this area is parallel to the axis of force, right? So this is how you are having this shear stress. Now sometimes what happens is due to this shear stress there is a change in shapes, right? So this particular gamma is known as shear strain, and as you are having that in axial stress and strain, we are having that relation sigma is equal to this E into E, right? So in the shear stress strain also we are having this relation up to that what we can say limit for this what we can say that that particular limit, elastic limit in case of the shear stress and strain. So as here it is elastic modulus, here it is this shear modulus, right? So this is how you can have this shear stress and shear strain having this relation tau is equal to this G into gamma, where gamma is shear strain. Now you already have idea about the relation between elastic modulus and the shear modulus. It is related with this E is equal to 2G1 plus mu. These are all the things which can be proved, but right, we are not going to spend time on this for now, right? Where this E is elastic modulus, G is shear modulus, and this is known as Poisson's ratio, right? Poisson's ratio is this lateral upon longitudinal, right? So here for some material value of mu is known, like carbon steel it is 0.29, grey cast iron it is 0.21. Generally this is lying between what we can say 1/4 to 3/4 or like that, right? So this is how you are having this magnitude of this Poisson's ratio. Now permissible shear stress, as you know, we are using this factor of safety. So permissible or allowable shear stress will be the failure or total shear strength upon factor of safety. So as we have seen for that prior already, we have discussed the factor of safety is that failure stress upon the working or allowable stress. So here this is maximum allowable stress, right, which can be calculated from the failure stress and factor of safety, right? So once you have idea about all these different types of stress and strain, then you can go for some more types of stress, right? We have seen till now that tensile and compressive stress, we have seen that the shear stress. Now there may be stress due to bending also, right? And in theory of pure bending in your this strength of material, right? Theory of pure bending is there, right? So what is there? That is sigma upon y is equal to m upon I is equal to E upon R, right? Very easy. Elastic modulus R is that radius of curvature, I is moment of inertia, m is that moment, and sigma is that stress, and y is the distance from the neutral axis. So from this, bending stress can be given by sigma b mb y upon I, right? And as you can see, whenever pure bending is there, you are having means on one side of the neutral axis, the nature of the stress will be compressive stress, and on the other side it will be tension. So in this particular case, on the upper half or on the upper side, you will find compressive nature of the stress, while in the lower half or lower side, you will have the tensile nature of the force, right? Based on that, you are having this bending moment diagram and all. And here this I is actually this area moment of inertia, right? So for some of the shape like rectangle, it is BD cube by 12, right? And for circular, here it is for rectangle, for circular it is directly 5 by 64 d raised to 4, right? But if you are having some irregular shape, then actually this IXY can be calculated with this y square dA, right? And here this figure shows that parallel axis theorem, in which you can calculate about any parallel axis to the centroid of the component. Like if you want to calculate about that Ix1, then it will be whatever about its the center plus ay1 square. Like that you can calculate about any axis, any parallel axis, right? So this is how you are having this stress generated because of this bending of the component. So this is how you are having this kind of stress is acting or present in your machine element. Next is this torsional moment. So again, if you remember that theory of pure torsion in your strength of material, so theory of pure torsion is what tau upon r is equal to T upon G is equal to G theta by L, where G is shear modulus, theta is angle of twist, L is the length, then T is torque, J is polar moment of inertia, right? Then R is that distance, and tau is again shear stress. So here this tau can be considered as this torque into radius upon this polar moment of inertia, right? So this is how you can have this different types of stress generated, right? And this theta can be calculated if you use this relation, this T upon J is equal to G theta by L, and if you replace it with this T with this G J theta by L, right? Then you can find the value of theta, right? After putting the values of this polar moment of inertia for different cross section, you can calculate that theta for different cross section, right? So this is again one type of stress which can be present in your machine element, like this torsional moment, stress due to torsional moment. Previously we have seen that stress due to bending moment. Now sometimes eccentric loading is present in your component. So if there is any eccentric loading is present, then as you can see in the figure, this figure A is the given condition actually, where you are having an external force acting at a particular distance from the axis, or we can say that central axis of the component. So in this case, what is going to happen is this particular external force is going to generate that force P by A. That is true, right? But apart from this, it is also generating that moment, that P into E. So once this moment is also present, then what is going to happen? Can anyone tell? If this moment is also present, then which other stress is going to come into picture?
Bendings.
Yeah,
So
so
tension
yeah,
passive.
bending stress, right? So this bending stress is, we have just now seen, that is mby upon I. So this pey upon I will be another stress which needs to be taken care because of this eccentricity. So that is why here they have mentioned that sigma will be equal to this p by a plus or minus this pey upon I. And why this plus or minus sign is there? Because as we know, in bending, both the nature of stresses are present, tension and compression. That is why at some place it will be added and at some place it will be subtracted based on the nature of the stress. So this is how eccentric loading will be considered. So once you are done with this eccentric loading, then we can go for some very simple problem. So before going to this problem, as mentioned here, design of simple machine parts, right? So what are the things you are going to consider when you go for designing any simple part? So the very first thing is you will analyze that what are the different types of stresses acting on the component, right? Approximately you will calculate those stresses and all, right? So you are not going to consider all the things, right? Like you are going to, you may neglect the stress concentration present and all, but at least you are going to calculate what are the different types of stresses acting on the component which you are designing. Then you must have idea about the allowable stresses, right? Now from where you are going to get these allowable stresses? That is going to be available from that a simple tension test must be performed on the material from which you are going to make your component, and those tension test is going to give you data about its yield strength, its fracture strength, ultimate strength, and its percentage elongation, its what we can say, Young's modulus, and all other things will be achievable through that tension test. So before going for design, you must have idea about the various stresses acting on it. You must have idea about the material from which you are going to make that product uh, are having which strength, what are the different magnitude of all those strength, yield strength, and this fracture strength and all, right? And then you have to finally have idea that which kind of failure theory you are going to apply. We will discuss this different types of theories of failure, but you also have to have idea about which failure theory you are going to apply, right, while designing your component. So once you have idea about this simple design procedure, then you can, I guess, attempt this simple problem. It is mentioned here, like these two plates subjected to a tensile force of 50 kilonewton are fixed together by means of three rivets as shown in the figure. The plates and rivets are made of plain carbon steel 10C4 with a tensile yield strength of 250 Newton per mm square. The yield strength in shear is 50% of the tensile yield strength, and the factor of safety is 2.5. Neglecting stress concentration, determine the diameter of rivet and the thickness of plates. So I guess you can try and attempt this question. Can you try? Hello.
Yes, sir.
Yes, sir.
Yeah, so please try. So what is given to you is this force, which is 50 into 10 raised to 3 Newton, right? That is given. Then this yield strength is given as 250 Newton per mm square. Then factor of safety is given as 2.5, right? So, and one more thing is mentioned as this yield strength is this 0.5 times the tensile strength. Yield strength in shear is 0.5 times yield strength in tension. So from this, maximum tau can be SSY upon vector of safety, right? So now this 0.5 into SYT means this 0.5.
Sir, here the yield strength can be considered as a failure stress.
Sorry.
Here the yield strength is considered as the failure stress.
See, here we are having two different stresses acting on two different components. For rivet, you are having shear stress, right? So you will consider that shear strength, shear yield strength. This is shear yield strength, and this is tensile yield strength. Both are yield strength only, right? But for the failure of plate, you will consider tensile stress, because this plate is experiencing this tensile stress while this rivet is experiencing this shear stress. So you will consider two different things for two different components, right? So for diameter of rivets, you will consider the shear strength or yield shear strength, and for the thickness of plate, you will consider this tensile yield strength. So here,
Yeah.
if we start with this rivet, then you need to have idea about the shear strength, which will be available from this shear yield strength upon this vector of safety. So it will be, I guess, 50, right? This will be 50. Yes or no?
Yes.
Yes, sir. Yes, sir.
So once you have this tau max as 50, then next you can consider the area on which this stress is acting. So area will be 3 rivets are there, so 3 into pi by 4 d square, right? And into force, right? Sorry, into this stress will be equal to force, because this stress is equal to load upon area, right? So this area into stress will be equal to the force. So now in this you are having this tau max, you are having the value of p, so you can calculate d. So 3 into pi by 4 d square into tau max is 50, and this p is given as 15 to 10 raised to 3, so which will give you d is equal to what?
20.6.
Yeah, so this is 20.6, or you can consider 22 mm, right? So as you have considered this shear stress or shear strength for your design of rivet, for design of your plate you are going to consider this tensile strength, right? So as tau max you have calculated from that SSY upon factor of safety.
Hello.
Yeah.
Sir, regarding D, 20.6 mm, how did you approximate it as 22 mm?
Actually what happens is you will have some table, right, for the rivet diameter. So there is some standard, so you must be having that standard table. So after 20.6 the next available diameter may be 22 mm, so that is why I have rounded it off to 22 mm, because each and every size may not be available for the diameter, no? It cannot be like starting from 1 mm to whatever number we want, right? It may not be available in all the size, so it may not be available for 21 mm, so that is why I have rounded it off to 22 mm in place of this 21 mm. Did you get this?
Okay, sir. Thank you, sir.
Yeah. So here this tau max as you have calculated from this SSY upon FP, and I guess for this standardization also there are some series and all they are using. I guess you must have studied some R series or what, I don't exactly remember, but they are using it for manufacturing with certain dimensions and all. So there is a different thing, right, which is known as that standards, right? So okay, let us come back to this. So as you have calculated this tau max from this SSY and FS, sigma t can also be calculated from that SYT and FS. So SYT you are having already as 250, and factor of safety is 2.5, so 100 Newton per meter mm square will be your sigma T. So once you have sigma T, again you can go for that sigma T into area on which it is acting. So here area will be that whatever width minus 3 times the diameter of the rivet, right? Because let me show you that particular figure. Here you can see this is the width, right, W. So the minimum area you need to consider when you are designing. So minimum area will be along this line, right, where you are having this W minus 3 times this diameter. This is the diameter of one rivet. So you are having 3 rivet. So W minus 3D is the least area on this plate, right? So least dimension along the length. So area will be this length into the thickness of the plate. So basically if you go for this particular cross section, then your plate may be having this area as W into T, right? Because here full width is available in this region, whatever I have drawn. So W into T may be the area in this cross section. But when you take this cross section, as it is mentioned here, XX along XX, so this 3D must be subtracted from the full width W. So W minus 3D into thickness will give you area, right? So this will give you area. So sigma T into this area is equal to P. So again sigma T you have calculated as 100, W you know 200 minus 3, rivet diameter you know 22, thickness of plate you have to calculate, P you already know 15 to 10 raised to 3. So this will give you this thickness. So thickness is what? Can you tell me?
सर 3.73 के आसपास है।
3.73 can be converted or can be taken as 4 mm. Okay, so is it clear? Hello.
Yes sir.
Okay.
Yes sir, it's
Okay,
clear sir.
okay. So now let us go to some next uh, topic, and that is this principal stresses.
So we were considering the rivet, so that's why we take the shear yield stress, and if you are considering the sheet, then I will be taking the other one.
Sorry, can you please repeat?
We were focusing on the rivets, that's why we take the shear yield stress as the failure stress, and if you're considering the sheet, whether we consider the failure stress as the shear stress.
See, actually, in case of that previous example, here, as I have told you, in case of rivet, there is a what you can say shear stress acting, right? Because as you have seen here, in case of this shear stress, as you can see, in case of failure of this rivet, shear stress is responsible. So whenever you are designing this rivets, the shear stress you are going to consider. And in case of this plate, this nature of stress will be there. This one, this kind of this tensile nature of stress will be present whenever you are going to consider about any plate, right? So this is only 2D plate, right? It must be having some its thickness also, right? So thickness will also be there. So if you are going to take cross section here, then it may be like this, I guess, like this. You can have the, what you can say, direction of this tensile stress. It is perpendicular to the area on which it is acting. But I guess here it is not that clear. 1 second. So if you go for So here if it is going to act like this, right, the sigma t, so the area on which it is acting, it is perpendicular to this force. Are you getting what I am trying to say? In case of plate, it is perpendicular. Hello.
Yes, sir. Yes, sir.
So is it clear?
Yes, sir.
Okay. So now let us go to this.
Sir,
Yeah.
sir, as you said, there are standard values of diameter of rivets.
Huh.
So, do we have to remember the table
No,
because the
no,
table is
no,
not
no,
given?
no, 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 not at all. It is not required to remember the table and all. It will be there with you, right? And in case of these exams, the whatever options are there will be definitely what we can say near to whatever answers you are getting. And in actual practice, when you are going to design any component, you will design any component with a design data book. So with
Okay.
the data book, you can take the values from those design data book. You need not to memorize or remember any of these kind of things. Okay.
Yes, sir.
Okay. So now let us go to this principal stress. I guess this is state of stress, right? For a 2D, state of stress is mentioned here, right? So this is your Mohr's circle. You will see this different things one by one, right? And here it is stress on oblique plane. So here this is normal stress and this is shear stress, right? So this sigma is normal stress and this tau is shear stress, right? So here, as you know, and I guess your strength of material, you all must have written this normal stress and shear stress on those oblique plane as this sigma is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Similarly, tau s, this minus sigma x minus sigma y by 2 sin 2 theta plus tau xy cos 2 theta. Now in order to get the maximum normal stress, you can differentiate this sigma and equate it to 0, which will give you this 2 theta is equal to 2 tau xy upon sigma x minus sigma y. So this theta will give you two value, and according to that you will get this sigma 1 and sigma 2 as sigma x plus sigma y by 2 plus or minus under root of sigma x minus sigma y by 2 square plus tau xy square. So these are known as principal stresses, right? So where shear stress is 0. So these are principal stresses can be calculated with this particular equations, and it will be at those two values of theta which will be available from the above equation of tan 2 theta. Similarly, this as we have discussed, these are principal stresses, right? As you have calculated this maximum normal stress, if you want to calculate that maximum shear stress, then you need to differentiate that tau and need to equate it to 0. So in that case, what you will get is tan 2 theta is equal to minus sigma x minus sigma y upon 2 tau xy. So once you get this, again 2 theta will be there. So again when you use those two different values of theta, you will get your maximum shear stress, where this tensile stress will be considered as 0. In that case, this a particular tau max will be available from this sigma x minus sigma y by 2 square plus tau xy square, right? So this is nothing but maximum shear stress. Previously it was maximum normal stresses. So this is how you can have this maximum shear stresses and maximum normal stresses. So shear stress you are going to consider positive clockwise and negative anti-clockwise, right? So this is how you are having this principal stresses. And I guess before going to this next slide, I guess you must have idea about this Mohr circle also. So what basically you are going to do for plotting this Mohr circle is you may be provided this state of stress, right, like sigma x, sigma y, and then tau yx and tau xy. So what is this tau xy and tau yx is actually whenever you are having any element. Suppose if you are taking this element, right, let us take this element. So in that case this tau xy and tau yx and all these things will be mentioned based on there is a specific meaning of those subscript x and y. Let us see that actually if you tell this is x, this is y, and this is z, then if it is plotted like this, it means it is considered as tau xy, where x represent the axis to which the plane is perpendicular and y is the direction, right? So it is placed on the plane perpendicular to x, right? So it is related for plane and this y is for direction. So it is perpendicular to that x-axis. This plane is there in which this tau xy is present, and it is towards the y direction. So suppose if you are having any shear stress in this direction, then it will be tau xz, right? Similarly, if you are having any this particular stress, then can anyone tell me what will be this particular force, or sorry, stress?
Tau yx.
Yes.
Tau yx.
Yeah. So this is tau yx. Similarly here you may have tau yz, like that, and it can be proven that tau xy is equal to tau yx, right? So now, having these things in mind, what you can do is you can see how this Mohr circle is plotted. So for that, if this state of stress is given, the sigma x, sigma y, tau xy, then you can first plot this. This is sigma x, this is sigma y, right? Then this is tau xy and tau yx. So once you are done with plotting all this, what you can do is you can join this D and B, right? So it is going to cut at E to your this normal stress. Basically this Mohr circle is plotted on this normal stress versus shear stress, right? So here you can then join this point T and B, which is going to cut at E. So once you are done with this, then you can take E as center and DB as diameter, and then you can have your full circle. So once you are going to do that, then you will have this maximum and minimum normal stress on your that particular axis of normal stress, the sigma 1 and sigma 2. Similarly, you will have maximum shear stress like this. This is maximum shear stress. This EH is your maximum shear stress. So like this you can have the construction of Mohr circle. Once you are done with this, then we can go for this.
Sir?
Yeah.
Sir, when does the condition of plane stress arise in practical situation?
Plane stress is going to arise when you are having generally stress is acting on all the three directions, right? Sigma 1, sigma 2 and sigma 3, right? Or sigma x, y and z. So whenever any of the stress is going to be 0, right, sigma 1 or sigma 2 or sigma 3, right, is going to be 0, that is known as plane stress. And plane stress is generally found in the application like sheet metal forming and all. right? In sheet metal forming, in deep drawing, right, whenever you are having this punch and you are having this sheet, right, which is going to be deformed, right? So whenever you are having this kind of deformed sheet, then actually in this region the thickness of sheet will remain almost same. It is not going to be changed because this is a plane stress region where stress is not acting along the third direction. Are you getting what I am saying?
Yes, sir. Yes, sir.
Similarly, plane strain condition is also there. So plane strain is whenever any of the strain E1, E2 or E3 is 0, right? In that case it can be considered as plane strain. So whenever any bulk forming operation is there, right, like forging or rolling, in that case you are having this plane strain condition, because in rolling, if you remember, you are having this heavy rollers and all, right, and you will have this strain, this reduction of the sheet thickness from from initial to final. So whenever you will have this initial to final sheet thickness, then it will be having that strain in this both direction, which is in this plane, but along the third direction, means along the width which is perpendicular to the plane of the screen, right, along that width direction, that strain will almost be 0. So that is why that is known as plane strain condition. And remember, in plane stress, only stress is considered as 0. Strain will be present in all the 3 direction almost, and in plane strain condition only strain is considered as 0 in the third direction. Stress will be remaining in all the 3 direction mostly, right? So this is how you are having this plane stress and plane strain conditions. Okay, is it clear?
In, in punching, there is shear stress that is on the end sides.
Sorry.
That in punching, I mean the sheet metal punching that you have drawn, there is a shear stress on the ends, isn't it?
It will be through that shear. Yeah.
So the shear stress
Sir,
is
actually,
different
no. Sorry. When in case of deep drawing, you will not have any shear, I guess. It is biaxial stretching and all in case of this deep drawing. Shearing will be there when you go for blanking and all. In blanking operations and all, you will cut your material through that shear. In case of deep drawing, it is biaxial stretching and all.
Okay. So, in punching, there will be.
In punching, it will be. In punching, you may have that shear. In punching and blanking, where you are cutting the material, in that case, you may have that shearing and all.
So this rolling and deep drawing will be considered as the plane stress, isn't it?
Sorry.
The case of deep drawing and rolling will be considered for the plane stress.
No. Deep drawing is plane stress. Rolling is not plane stress. Rolling will come under, I guess, plane strain, because it is bulk forming operation.
Okay.
Okay.
So in case of plane stress, will there be bending as well?
Sorry.
In case of plane stress condition, will there be bending and torsion also, sir?
See, bending and torsion, and these are all together a different concern, right? This thing is related to when there is stress absent in any of the 3 direction, right? So that there may be bending stress or torsional stress. That is altogether a different thing. Are you getting what I'm trying to say?
Yes.
Okay, so the nature of stress is different than what we are discussing.
Sir, in deep drawing, won't there be any shear stress?
In deep drawing, I don't think so. There is.
Sir, because if there is sigma x and sigma y, then according to the formula, shear stress should have a magnitude.
see here, shear stress will not be there in case of this deep drawing, I guess, because there will be tensile and compressive stresses will be there in case of deep drawing, right? Somebody is asking about lecture tomorrow. I have no idea regarding tomorrow's lecture, Rayansh. Okay, okay, so let us continue here. So now see, this is whole together a different topic, right, which we have started discussing, like the analysis of metal forming. In that we can discuss that what are the different types of stresses and what is the nature of stresses acting in those particular situation. So we can discuss it, but now I guess we should continue with what we are trying to discuss today. So can we move forward with this, if you say? Okay.
Yes, sir. Yes, sir. Yes, sir.
Okay, so let us continue on main agenda, right? So what we are going to see now is this theories of failure, right? Theories of failure. So there are various theories of failure, right? Whatever we are going to discuss is this elastic failure theories we are going to discuss. So what this theories of failure is, actually whenever as we have discussed, there are various types of stresses like shear stress, then tensile stress, compressive stress, bending stress, torsional stress, right? So whenever any machine component is under working condition, there are combined stress acting on that particular component, right? Combined state of stress will be there. So it is difficult to produce this kind of combined state of stress for each individual component and then to decide how we can keep the limit of stress for that particular material. So what we are doing is we are performing a simple tension test, right, as I have told earlier. A simple tensile test we are doing, and then we are defining material properties from that tensile stress. Material properties like Young's modulus, then its yield strength, its ultimate strength, right? Then this percentage elongation, right? Then toughness, resilience, right, and so on. Like then it's like this we are going to calculate all these things from that simple tension test. So there is a difference between that this strength and stress, right? Strength is related to materials property, while stress is uh, generated because of the externally applied load. So there is a difference between strength and stress. Strength is considered as property of material. So this while discussing these theories of failure, what we are going to consider is the data which we have obtained from a simple tension test, right? So based on this, there are various failure theories, right? So there are like maximum principal stress theory, right? It is also known as Rankine theory, right? Then
So the yield strength value and yield stress value will be same.
sorry,
Yield strength value and yield stress value. Will it be same?
see, there is a basic difference in strength and stress itself, as I have told you, right? So
Observe.
stress and strength both are different. Strength is coming under this material property, right, while stress is generated because of externally applied load. So you cannot actually use the term yield stress. Yield strength is the right term, right? So stress generated in any component, please mute yourself. Stress generated in any component or element may be greater than or less than or equal to yield strength. So is it clear? Hello?
Okay, sir.
Yeah. So this
Sir,
maximum.
when we say strength, like generally we mean yield strength.
Sorry?
When we just say the strength of a material, which means like we are saying about mentioning about the yield strength only.
No, it cannot be generalized, because see, in case of this brittle material, you are considering ultimate strength, right? For ductile, it is yield strength, but for brittle, you are considering ultimate strength, right? Or ultimate tensile strength. So when you simply say strength, it cannot be identified whether it is yield or whether it is ultimate tensile or what. So that you have to be specific which strength you are talking about, whether yield strength or ultimate strength or fracture strength, like that. Okay.
Yes.
So,
Sorry.
the yield strength will be the stress corresponding to the yield point.
Yield strength is stress. Yeah, stress corresponding to yield point. Correct.
Okay, so we cannot say that yield stress. It's a yield strength only.
Yeah, yield strength is the correct term.
Okay, sir.
Yeah. Stress generated may be equal to, less than, or greater than the yield strength, like that. Okay.
Okay, sir.
So now after this, there are various this theories of failure. This maximum principal stress theory, then maximum shear stress theory, which is known as that Coulomb, Tresca, and this Guest. Right. These are the scientists who have invented this theory. So distortion energy theory is von Mises and Hansen. Right. So distortion energy theory, then this maximum strain theory. Maximum strain theory is from that Saint Venant. Then this maximum total strain energy theory. And it is so these are various theories. From this we are going to focus on these three for now: maximum principal stress theory, maximum shear stress theory, and distortion energy theory. Right. So if we go for one by one, right, and first is this maximum principal stress theory. So for that, actually here is what we can say, the envelope for this is given. We will come to this later. Before that, if we start discussing about this MPST only, then what maximum principal stress theory says is failure is going to occur failure is going to occur when maximum principal stress is going to reach the yield or ultimate strength is greater than the yield or ultimate tensile strength, right? Yield or ultimate strength, as we have discussed. In case of ductile, it is yield. In case of brittle, it is ultimate strength, right? So basically what maximum principal stress theory says, whenever we are having any machine component which is under operation, in that particular component failure is going to occur when the maximum principal stress generated during the working of that component is going to cross the yield strength or ultimate strength of that material. Is it clear? Hello?
Yes, sir. Yes, sir.
Right.
Yes,
So
sir.
yeah, so now,
So,
yeah,
for the
so now
material,
if we are having this three let us say three different stresses are acting, right? Normal stresses, that is principal stress. So let us say the sigma 1 is greater than sigma 2 greater than sigma 3. So what we are interested in is among this principal stresses, whatever is the maximum principal stress, if it is greater than or equal to this yield strength or ultimate strength, then the failure is going to occur. If you are going to consider this what we can say factor of safety, then this sigma 1 is equal to this SYT upon factor of safety, or this sigma 1 is going to be ultimate upon factor of safety. And here we have considered it under this tension only, right? Yield strength under tension. If you go for this compression, then it can be also written as this yield strength under compression, or ultimate strength under compression, right? Like this. So
सर एक पूछना है।
hmm,
सर मतलब जो कंप्रेशन टेस्ट, सिंपल कंप्रेशन टेस्ट और सिंपल टेंशन टेस्ट, इनके ग्राफ को जब कंपेयर करेंगे तो
hello.
हाँ हाँ सर, सर सिंपल कंप्रेशन टेस्ट एंड सिंपल टेंशन टेस्ट के ग्राफ को कंपेयर करेंगे तो सर एक बार कंपैरिजन करके बता दीजिएगा कि
See,
क्योंकि उसमें तो
in case
different
of
कुछ होगा।
ductile material, it is almost same. This yield strength under this tension and yield strength under compression is almost similar. But for brittle material, this yield strength under this compression is greater than yield strength under tension, right? So in this brittle material it is not same, right? So suppose if you consider tension test, right, for a brittle material, then it may be like this, right? For what we can say it's this strength or yield, or it may be in that case actually it will have that ultimate strength only, right? So ultimate strength for this in compression will be greater than ultimate strength under the tension. So if it is breaking under compression at a particular point, right, then under tension it will be even less, like this, right? So this is higher than this one. For brittle material, compression is higher than tension for brittle material. Is it okay?
Yes sir, yes.
Okay. Now if we go for region of safety, that is what is drawn on that figure, region of safety for this maximum principal stress theory, right? So you are having this sigma 1 and sigma 2 plot, right? Sigma 1 and sigma 2. So suppose we can plot this region of safety. We are considering sigma 3 as 0, so we are considering biaxial state of stress, right? And for that we are plotting this region of safety according to maximum principal stress theory. So we can consider 4 different cases. In first case, if sigma 1 is greater than sigma 2 and it is having the tensile, then it can be considered, let us say this may be the SYT. So there must be a line which is passing through this point. So sigma 1 is equal to this plus YT, it is the limit, right, for this components to get failed. Similarly, if sigma 1 is greater than sigma 2, and this under compression if we are talking, then for compression we are plotting it on the negative side. So here it will have this sigma 1 is equal to minus s by c. So this will be the line, right, apart after which failure will start. Same way you can go, this both the lines are drawn, this first and second line, this first and second both are drawn with an assumption that sigma 1 is greater than sigma 2. Now if we go for the sigma 2 is greater than sigma 1, then in case of tension you will have a line here which will tell that sigma 2 is equal to plus s by t, and in compression you will have a line here which will tell sigma 2 as minus s by c. So this is the third and fourth case where sigma 2 is greater than sigma 1. So basically this is what we can say, this is the region or envelope we have come up with after considering different conditions. So if your component is working and it is having stress at any point right inside this envelope, then your component is fine. It means any point means if it is having the sigma 1 value is this and sigma 2 value is this, right? Similarly it is here, so sigma 2 value is this and sigma 1 value is this. Are you getting what I'm trying to say? It may be having sigma 1 value is this and sigma 2 value is this. It is fine, right? Anywhere in this envelope it is not going to
So in this region, both sigma 1 and sigma 2 both are less than their ultimate strength.
yeah, yes, definitely, then only it will not fail, otherwise it will fail, right?
Yes.
So if any point lies outside this envelope, then you will have failure because this particular stress is exceeding the limit. So this is failure region. Okay, this particular point you can consider under failure region. So this is how you are having this maximum principal stress theory. Now if you go for the next one, that maximum shear stress theory. Oh, one more thing is there, I guess, in maximum principal stress theory, and that is, no, I guess that is it for here, right? As you can see, whatever we have discussed is mentioned here. But one interesting thing is, see here it is almost like a square, because almost s by t and s by c are considered equal, right? Which is the case for actually ductile material, right? But for brittle material, actually what is going to happen is, for brittle material,
सेंटर ऑफ स्क्वायर मतलब शिफ्ट करेगा
what is going to happen for brittle material? Hello?
सर सेंटर ऑफ स्क्वायर शिफ्ट कर जाएगा थर्ड क्वाड्रेंट में
Yeah. Why? Because in case of this sigma 1 and sigma 2, in case of brittle material, its tension limits are very less compared to its compressive limits. So when it comes to this tension line, this and this, it will be less than those compression lines, like this, right? So this is how this is SYT, here also SYT, right? While here, see, this is SYT for sigma 2, this is SYT for sigma 1, here it is SYC for sigma 1, and here it is SYC for sigma 2. So like this it will be expanded towards the compressive side in case of brittle material for maximum principal stress theory. And maximum principal stress theory is generally applied to brittle material only, right? So this is how you are having change in case of this brittle material. Now if we go for maximum shear stress theory, hello,
सर कंप्रेशन और टेंशन में जो यंग्स मॉडुलस उसमें चेंज मतलब क्यों नहीं आ रहा
sorry,
है सर कंप्रेशन और टेंशन में जो यंग्स मॉडुलस है ब्रिटल मटेरियल का उसमें चेंज आएगा क्या
I guess it must be same Young's modulus, but still I will check, right?
ओके सर
Okay. So
Sir,
here,
probably the Young's modulus just decides the slope only.
yeah, that is the slope only. So I guess it should not affect, but still we will see if there is anything, right? In what we can say, change is there. Actually, Young's modulus is given at some atomic level stiffness and all. E is given by some that stiffness of those atomic level, and then at atomic radius level it is defined, I guess. So it should not get changed, but still I will check. Okay.
ओके सर नेक्स्ट
Sir, I have a doubt.
Yeah.
Sir, generally when we say maximum applicable stress, is
Ah.
it a material property or
Sorry, maximum allowed.
maximum applicable stress? That is maximum stress a body can withstand without failure.
That is material property, right? Whatever maximum stress a body can sustain without failure, that is material property. That is strength of that material.
Okay, sir.
Okay. Now,
So for the previous figure, the sigma 2 is the stress in y direction, isn't it?
sorry.
For the previous figure, the sigma 2 is for the stress in y direction.
Yeah.
So then why if we are considering sigma 2 as more or anything, that's the graph is area is more shifted towards the bottom.
Sorry, can you repeat?
The area of the graph is shifted more towards the bottom portion. Is the sigma y is taken as more or anything?
It is also shifted towards negative left also, no? Negative x also it has shifted. Negative x also it has shifted like that.
Okay, sir.
So here in maximum shear stress theory, as previously we have seen that in case of maximum principal stress theory, the failure is going to occur when that maximum principal stress is going to exceed the yield strength or that ultimate strength of a material which is under tension test, right? Then that failure will occur. So here in case of this maximum shear stress theory, failure is going to occur when maximum shear stress at any point is going to be equal to the maximum shear stress in the standard specimen of that tensile stress, right? So now maximum shear stress of that tensile specimen is sigma 1 by 2, right? This has come from this Mohr circle, because in tension test you will have only that uniaxial stress, so sigma 1 will be there, sigma 2, sigma 3 will be 0. So if you plot the Mohr circle, you will have this tau max is equal to this sigma 1 by 2. So sigma 1 is that normal stress, right? So tau max is nothing but that yield tensile strength by 2, right? And if you go for all the what we can say 3 plane, right? 1 second. So if you go for all the 3 plane, then this tau 1 2 may be considered as the sigma 1 minus sigma 2 by 2. Tau 2 3 can be considered as sigma 2 minus sigma 3 by 2, and tau 3 1 is sigma 3 minus sigma 1 by 2. Now here in our case, what we have seen is this tau max is coming as SYT by 2, right? So if we write what we have written just now, like sigma 1 minus sigma 2 by 2 into this SYT by 2, right? So this gives sigma 1 minus sigma 2 is equal to SYT. You can use factor of safety also if you require, but we can write like this for all the three planes, like sigma 2 minus sigma 3 is equal to also SYT, and in case of compression it can be written as sigma yield under compression, right? So sigma 3 minus sigma 1 is equal to again SYT minus SYC, right? So once you have this, now this is triaxial state of stress. If you go for biaxial state of stress and you make sigma 3 is equal to 0, then what you can write is sigma 1 minus sigma 2 is equal to this plus or minus SYT. If we are considering this tension only, then sigma 2 is equal to plus or minus SYT, and then sigma 1 is equal to plus or minus SYT. So once you are done with this, then what you can do is you can plot this region of safety with these equations, right? These are equations of this line, right? When you write this equations, right, then you can plot the region of safety from this
Hello, sir.
line
Excuse me,
equation. Yes.
sir. How you have written that sigma 2 and sigma 1 same when, and also their subtraction is also.
See, I simply made this sigma 3 is equal to 0. Are you getting? Hello?
Yeah, yes, sir, yes, sir. Okay.
Okay.
Understood.
So from that this equations has come. So this all equations are going to help in designing or defining this region of safety. So if I plot this sigma 1 and sigma 2, again the sigma 1 and sigma 2, then what is going to happen is, see, sigma 1 is equal to plus or minus SYT, and sigma 2 is equal to plus or minus SYT is similar to that maximum principal stress theory, which is going to give this what we can say quadrant second and quadrant first and quadrant third. So in second quadrant and fourth quadrant, it is going to follow the different equation, this envelope. This is known as shear diagonal, because at those points sigma 1 will be equal to minus sigma 2, which is known as condition of pure shear. Now this, as we have considered that sigma is equal to plus SYT, this sigma 2 is equal to minus SYT, this is sigma 1 is equal to plus SYT, this is sigma 1 is equal to minus SYT. Now if you consider this as minus SYT, then this equation is sigma 1 minus sigma 2 is equal to minus SYT, because here sigma 1 is there, sigma 2 is 0, and this sigma 1 minus sigma 2 is equal to minus SYT. Here if you consider as plus SYT, then this line is sigma 1 minus sigma 2 is equal to plus SYT. So this is how again you are having this envelope under which your stress points are safe, and if it lies outside, then it will be a failure region, right? This particular this is known as those failure points, right? So this is how you are having that region of safety in case of your maximum shear stress theory, right? You can see it here, right, as you can see here. So this is how.
Sir, is this due to the shear stress?
Sorry.
This MSST is applied generally for shear stress cases.
This MSST is generally applied for ductile material. right? MSST is generally applied for ductile material, right? And in MSST you are considering shear stress only, so that is the out of question, right, to ask about the shear stress.
जस्ट अ क्वेश्चन सर, ये जो shear diagonal है इससे मतलब क्या इसका यूटिलाइजेशन कर सकते हैं?
See, that is going to help us in finding the point, right? Because it will be the outermost point in case of that particular region in those quadrant. So by using that, what we can say, can you see my screen?
Yes sir.
Yes, sir.
Okay, so by using this equation, see this sigma 1 by sigma 2 is equal to minus 1 is also a line equation, right? Sigma 1 is equal to minus sigma 2, and you are already having this equation that sigma 1 minus sigma 2 is equal to plus syt. So by combining both this equation you can come up with this point G, right, because it is intersection of these two lines. So it will give you that particular point. If you put that sigma 1 is equal to minus sigma 2, means sigma 2 is equal to minus sigma 1 in this equation, right, from here to this equation, then sigma 1 minus minus sigma 1 will be equal to syt. So this sigma 1 equal to syt by 2, right? So this is how you will be able to find this point G. So that is why the shear diagonal is important, and shear diagonal is representing the pure shear condition, right? Pure shear condition, you know, right? On mover circle, pure shear condition means the sigma 1 is equal to sigma 2. So if you plot it on this mover circle, this sigma 1 and this sigma 2, so if sigma 1 and this sigma 2, means if you are having that sigma 1 2 is equal to this plus and minus sigma, it means sigma 1 is plus sigma and sigma 2 is minus sigma, then you will have this kind of mover circle. It is not sigma 2, it is the shear stress, sorry, it is that shear stress, right? So here, one second, right? So here this will be your mover circle, right? So this is condition of pure shear when this normal stress is, this is sigma and this is tau, right, in your mover circle. So normal stresses are this same in magnitude, only different in nature, tensile and compressive, which will give you this pure shear, right? And in pure shear this will be your condition as you have drawn that mover circle, and from this both line equation you are getting this final sigma 1 is equal to syt by 2, right? So this is how you are having that maximum shear stress theory. So actually this is that maximum shear stress, right? So that will be this ultimate tensile strength divided by 2. So basically this shear strength in case of this shear stress theory is nothing but 0.5 times this ultimate tensile strength. So this is how your maximum shear stress theory is giving this value of your maximum shear stress. It is 0.5 times the ultimate yield strength in the tension. Now once this maximum shear stress theory is done, then you are having this distortion energy theory. So distortion energy theory is actually considering that strain energy per unit volume must be in case of that application, whenever your component is under application, so failure is going to occur when that strain energy per unit volume is going to exceed the strain energy per unit volume at the point of failure in case of the tension test. So now first we have to see what is this strain energy? So actually this strain energy is this, if you are taking all the three direction, then strain energy is this 1/2 sigma 1 E1, sigma 2 E2 and sigma 3 E3, right, where this is stress and strain, right, sigma 1 and E1 respectively. So in this actually this E1 is given by is 1 upon E sigma 1 minus this Poisson's ratio sigma 2 plus sigma 3, right. So here E1, E2 and E3 are given with this same, right, sigma 1 plus sigma 3, and this E3 is 1 upon E sigma 3 minus mu sigma 1 plus sigma 2. So in other two direction this Poisson's ratio will take care, because it is that lateral and longitudinal stress both it is considering. So here this E1, E2, E3 will be given by this. Now if you put all these values in the above equation, your E will be something, your that strain energy will be something like this 1 upon this 2E sigma 1 square sigma 2 square sigma 3 square minus 2 mu sigma 1 sigma 2 sigma 2 sigma 3 sigma 3 sigma 1, right, like this you will get. Now actually this particular stress along all the three directions are having two components, that is deviatoric component, right, and this whatever we can say that which is going to change the volumetric what we can say, which is going to change the volume. So deviatoric component and this volumetric component will be there for each stress, right. So this sigma 1, sigma 2 and sigma 3 will have this three what we can say components, right. So this deviatoric stress is going to be responsible for the plastic deformation, right. So here this as the stress is divided into these two, the strain energy is also divided in this, right, this distortion and volumetric change. So this distortion and volumetric change is there, right. So distortion means there is no change in volume, right, only distortion is there, and UV means there is a volumetric change. So strain energy itself is divided in two parts, that one is going to take part in only this what we can say distortion, and the other is going to take place in volume change. So when you are considering only distortion, so the particular part which is related to only distortion and not going to change the volume, so for that strain will also be 0. So E1D, E2D and E3D will be 0, because it is not going to make any change in volume, so strain will be 0. So if no change in volume there, then the volume constancy is there, so E1D, E2D and E3D will give 0. Again E1D, E2D and E3D can be represented with this, right, sigma 1D minus this mu sigma 2D sigma 3D.
So can you say how will the difference distortion?
Sorry?
So how do they exactly differ, like distortion, volume change?
See, distortion is there is no change in what we can say volume, and change in only the shape, or let me draw this 1 second. Once I am done with this, I can draw that. So sigma 3D minus mu sigma 1D sigma 2D. So if you are having any object like this, right, so if you are giving distortion to it, then what is going to happen is simply the shape is going to change and not the volume, right? Are you getting?
Yes, sir. So this is change in
Distortion only.
shape, that is change in size.
There is no change in volume, right?
Yes.
So this is how distortion takes place, right? And the other part is responsible for volume change, right? Volumetric component, which is going to be responsible for volume change, right? So now if you put this values, right, sorry, then what is going to happen is, if you put this values E1d, E2d and E3d in this equation, then you will find this 1 minus 2 mu sigma 1d, one second, sigma 1d, sigma 2d and sigma 3d is equal to 0, right? So as you know that 1 minus 2 mu cannot be 0, means this component is 0. Sigma 1d, sigma 2d, sigma 3d is equal to 0, right? So if this sigma 1d, sigma 2d, sigma 3d is 0, then if you take this sum sigma 1 plus sigma 2 plus sigma 3 from this one, right, then you will have this 3 sigma v is equal to sigma 1 plus sigma 2 plus sigma 3. So basically sigma v is then given by 1 by 3 sigma 1 plus sigma 2 plus sigma 3, right? So once you have this values with you, then if you go for your uv, if you go for this uv, then uv is 3 times all this sigma v ev by 2, right? And ev can again be written as this 1 upon e sigma v minus mu sigma v plus sigma v, right? So basically this will give 1 minus 2 mu the sigma v, sigma v upon e, right? It will give this 1 minus 2 mu sigma v upon e. So if you put value of this that strain, volumetric strain in this uv, then you will get 3 1 minus 2 mu sigma v square by 2e. This is how you are having that value of uv. And as you know, value of sigma v is with you, that is 1 by 3 sigma 1 plus sigma 2 plus sigma 3. So if you put all these values, then uv will be equal to 1 minus 2 mu sigma 1 plus sigma 2 plus sigma 3 square divided by 6e. Right, now once you have that value of this uv with you, then you have calculated that u earlier, right? This value of u is with u, then similarly you have calculated uv. So once you have u and uv both, then you can mention this ut, that is u minus uv. So as you know, u and uv with u, so if you put all those values, what you will end up with is 1 plus mu upon 6e into the sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. Now for simple tension test, only sigma 1 is SYT, you know, and sigma 2 sigma 3 is equal to 0 because it is uniaxial tensile test. So if you put this value now in this equation, then what you will end up with is 1 plus mu upon 3e SYT square, right? So now once you have this ud is equal to 1 plus mu upon 3e SYT square, you can now equate this ud and this particular equation which you have got, right? So if you are going to equate this, then what you are going to get is this, once again, this UD for tension and general UD when you are going to equate, then you will end up with this 2SYT square is equal to this sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. So from this you will find that SYT is nothing but is 1 by 2 sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. Under root of this will be your SYT, right? Now if you are going to consider biaxial state of stress, then what will happen? Sigma 3 is 0, so in that case you will end up with this SYT is equal to under root of sigma 1 square minus sigma 1 sigma 2 plus sigma 2 square, right? So this is how you will get this equation, right? So basically this equation of ellipse, if you are going to open it, the sigma 1 square minus sigma 1 sigma 2 plus sigma 2 square is equal to SYT square. This is how you will get it, right, in case of this biaxial state of stress. If you will consider pure shear, right, then for pure shear, as you know, sigma 1 is equal to minus sigma 2 is equal to tau xy, right, and sigma 3 is 0. So for this, if you put the values in this above equation, then sigma 1 is equal to minus sigma 2, it means 3 sigma 1 square is equal to SYT square, which will give this which will give this SYT is equal to root 3 sigma 1, where sigma 1 is tau xy. SYT is equal to root 3 sigma 1, where sigma 1 is tau xy. So this is how you will have SYT is equal to root 3 tau xy, right? So this is how you are having this relation between this yield strength in shear and yield strength in tension. So basically your SSY can be calculated with this SYT by root 3. So it is nothing but 0.577 times SYT. In case of MSST it was 0.5T, if you remember, right? So this is how yield strength in shear is 0.577 times yield strength in tension in case of distortion energy theory or maximum distortion energy theory, right? So region of safety here is given from that equation of ellipse, right? X square minus xy plus y square is equal to a square. This you can equate with sigma 1 square minus sigma 1 sigma 2 plus sigma 2 square is equal to SYT square. So here for this ellipse, actually semi-major and semi-minor axis, semi-major and semi-minor axis is given with this root 2a and root 2 by 3a for this one, right? So similarly for this one, if you get, then this semi-major and semi-minor will be this root 2 SYT and root 2 by 3 SYT. This is how you are having in case of this maximum distortion energy theory. And one last thing, here also you will have that sigma 1 is equal to minus sigma 2 for that shear diagonal and pure shear, right, shear diagonal. So if you put this value, right, shear diagonal in this equation, right, which is mentioned above, so what you will get, you will again get that sigma 1 is equal to that SYP upon root 3. That is what we have already discussed. Now after having idea about all these three different types of theories of failure, Here you are having this comparison of theory of failure. So basically for ductile material you are using MSST and this distortion energy theory, while for brittle material you are using maximum principal stress theory. So MSST is simple, right, while DET is more accurate, right. So distortion energy theory is more accurate in comparison to MSST, and MSST is conservative also in comparison to distortion energy theory, because the envelope of MSST lies inside the distortion energy theory envelope. This ellipse is distortion energy theory, and that particular rectangle is that what we can say, this maximum shear stress theory, right. So it lies inside it, it means it is more conservative, while this maximum principal stress theory is this square. So sometimes it is dangerous to go with this MPST, because here in this particular region, right, if you see this region here, this region says that it is safe, right. If you see this region here, if any point is there, then MPST will say it is safe, but for ductile material it is not safe, because it is lying outside the envelope, both the envelope of MSST and distortion energy theory. So sometimes it is dangerous to go for maximum principal stress theory for this ductile material. Are you getting what I am trying to say?
Yes, sir.
Okay, so this is how you are having this comparison of this particular what we can say, different theories of failure. Yeah,
सर 1D and plus epsilon 2D plus epsilon 3D जीरो क्यों मान लिया था
sorry.
सर while deriving the equation for the maximum मतलब
This E1D, E2D, E3D, huh?
सर हाँ हाँ तब इसको जीरो क्यों मान लिया था
Because it is not going to make any volumetric change. That is why this E1D, E2D, E3D is equal to 0. There is not any volumetric change because of this distortion, stress and strain. Volume constancy is there.
Okay, sir.
Huh. So now let us go for the next one. So this is a very simple problem, right? So here the shaft of an overhang crank subjected to a force P of 1 kilonewton as shown in the figure. The shaft is made of plain carbon steel 45C8 and the tensile yield strength is 380 Newton per mm square. Sorry. The factor of safety is 2. Determine the diameter of the shaft using the maximum shear stress theory. So here you are asked to use maximum shear stress theory, because this plain carbon steel may be considered as ductile material. So what you have to do is you have to calculate this diameter. So for calculating diameter you have to have idea about the stresses acting on this component, and then you can apply any particular failure theory which is mentioned here, maximum shear stress theory, and then you can calculate diameter. So can you try it? Hello? Hello? Hello?
Yes, sir. Yes, sir.
Yeah. So can you see my screen?
Yes, sir.
So please calculate. So here what is given is P is equal to 1 kilonewton then SYT is equal to 380 Newton per mm square. Then permissible shear stress you can calculate from SSY, bond factor of safety, where SSY is 0.5 times SYT, bond factor of safety. So that is 0.5 into 380 divided by factor of safety, that is 2. It will give you 95 Newton per mm square, right? So once you calculate this, then you have to calculate bending moment and torsional moment, right? So what is the bending moment here? So if you consider this particular force acting at this point, then it will generate bending moment of P into this distance, this P into 250.
Bending or torsion?
For torsion, it will be this particular distance. This will be bending moment, right? Because you are considering this point A. So if we are considering this point A, then this force P is going to have bending moment equal to P into 250, and the torsional moment MT equals to P into 500. Okay. Hello.
Yes, sir.
Right, so once you have this bending moment and torsional moment, then you can calculate bending stress and torsional stress with this simple equation: sigma B is equal to mby upon I, and sigma, or you can say torsional stress, right? Sorry, so torsional stress, 1 second. So torsional stress we can write with that tau, that is mt r by j. So here, as you are seeing that circular cross section, so this is 250 into 10 raised to cube, right? Because P is 1 kilonewton, that is 10 raised to 3. So this is 250 into 10 raised to 3, y is d by 2, and for circular cross section I is pi by 64 d raised to 4. For tau it is 500 into 10 raised to 3 d by 2 divided by this pi by 32 d raised to 4, right? But both are coming same almost, right? Because here some same data is there almost. So this 2546.48 into 10 raised to 3 divided by d cube, that is Newton per mm square. This is stress. Now once you have both this stress with you, normal stress and shear stress, then you can go for this maximum shear stress. Once you have normal and shear stress with you, you can go for this maximum shear stress, sigma x minus sigma y by 2 square plus tau xy square. So which will give you this 2847.05 into 10 raised to 3 divided by t cube. This maximum shear stress equal to actually this 95. So it will give you this diameter 31.06 mm. Okay. Hello. So now if you are done with this, then we can go for some gate questions. So here we can see this is from gate 2014 S2 session 2. Consider the two sets of stress as shown in configuration 1 and 2 in the figure given below. From the standpoint of distortion energy, von Mises criterion, which one of the following statement is true? So you can use this von Mises criteria, right? So here von Mises criteria, you have to consider that sigma is equal to this full equation of that von Mises is sigma 1 minus sigma 2 square 1 by 2, sigma 1 minus sigma 2 square, sigma 2 minus sigma 3 square, plus sigma 3 minus sigma 1 square, plus 6 into sigma 1 2 sigma 2 3 sigma 3 1 square, like this. So the sigma 1 2 sigma 2 3 and sigma 3 1 are tau x y, tau y z and tau x z, right? So that is this tau sigma. Yeah, so with this equation you can calculate the resultant stress in both the cases. So this is tau x z and you can consider this as tau zx. Similarly here you can consider this as tau yz and this as tau zy, like that. Okay, hello. So
Yes, sir. Yes, sir.
so here you are having one of the normal stress and one of the shear stress is present in both the case. So in this case you are having that sigma 2 and this what we can say tau yz, but magnitude is same, right? Sigma 2 is equal to sigma and tau yz is equal to tau. Similarly in this case sigma 2 is equal to sigma and tau xz is equal to tau. If you put this value in this equation, what do
Sir,
you think? Both are
will-
same, right?
yes, sir.
सर पर ये जो आपने ये टाओ मतलब सिग्मा 1 2 प्लस सिग्मा 1 3 ये वाला तो सर प्रूफ में था ही नहीं.
Yeah, so we have not considered that, but actually it is there when we consider that shear stress also. We have not considered this while deriving this, right?
And sir,
Because
sir,
we have
specifically for
considered only that
for
biaxial stress of state. For that only we have seen that whatever we have seen, that sigma 1 square minus sigma 1 sigma 2 plus sigma 2 square is equal to this syt square, right? So 2 syt square. So we have not considered that sigma sorry, we have not considered those shear stresses and all. If we consider all that, then this will be the equation for this von Mises.
सर पर जो सिग्मा 1 सिग्मा 2 सिग्मा 3 है ये तो मैक्सिमम प्रिंसिपल स्ट्रेस है और जहां मैक्सिमम प्रिंसिपल स्ट्रेस होता है वहां तो शियर स्ट्रेस होता ही नहीं है.
Sorry,
Sir, since sigma 1 sigma 2 and sigma 3 are maximum principal stresses और
see,
मतलब सर जहां
actually this is this sigma x minus sigma y minus sigma z and sigma z minus sigma x, right? Because this is sigma y, right? It may not be the principal stress here, this in this case. So here in this equation, actually this sigma is this 1 by 2 in bracket this sigma x minus sigma y square plus sigma y minus sigma z square plus sigma z minus sigma x square, right? And plus this 6 into this tau xy plus tau yz plus tau zx. So it is also having its proof, but we have not considered here in this lecture, right? So it is
okay sir.
different. Okay.
Sir,
Yeah.
one thing I have to ask you that for distortion theory there are except von Mises there are so many. So for gate should we follow only von Mises theory?
Yeah. one message theory should be followed.
Okay.
Okay, so after this let us go for the next question. This one here, it is from 2014 session 3. Which one of the following is not correct? Can you read the options and tell me? Anyone?
B.
Correct. B is incorrect, right? Because intermediate principal stress are ignored when using maximum principal stress theory, right? Correct. Because we are only considering sigma 1, right? Whatever is the maximum of this, means we are only looking at this sigma 1, which is maximum. We are not going for intermediate stresses. While the second is saying that maximum shear stress theory gives the accurate result. It is not correct, right? Distortion energy theory gives the most accurate result, right? As per maximum strain energy theory, failure occurs when the strain energy per unit volume exceeds a critical value. That is also correct. And as maximum distortion energy theory, as per maximum distortion energy theory, failure occurs when the distortion energy per unit volume exceeds the particular critical value, right? So here in maximum strain energy, it is that maximum strain energy full which is going to exceed, while in case of distortion energy theory, only this distortion energy per unit volume is going to exceed a certain value. So that is the difference between those two, right? Now next is this one, 2014 session 4. A shaft is subjected to pure torsional moment. The maximum shear stress developed in the shaft is 100 megapascal, right? Then the yield and ultimate strengths of the shaft material in tensions are this 300 megapascal and 450 megapascal respectively. The factor of safety using maximum distortion energy theory, right? So can you try this question?
Root 3, sir.
Sorry?
Root 3.
Okay, anyone else? Here actually you can go for this, right? Sigma 1
Yes, sir.
square.
Root 3. Root 3.
Okay. Sigma 1
Then
square, sigma less than or equal to this sigma y by n square, right? S by d by n square. So if you are going to put the values, see here it is under pure torsional, means pure shear. It means what? That sigma 1 is equal to sigma 2 is equal to, actually sigma 1 is equal to minus sigma 2. So it means that sigma 1 is equal to 100 and sigma 2 is equal to minus 100. That we have seen that Mohr circle of that pure shear, right? So as this is tau max is given as 100, right? So this sigma 1 and sigma 2 will be plus 100 and minus 100, right? So from that the sigma 1 and sigma 2 has come. So if you put sigma 1 and sigma 2 as plus and minus 100, then you will have this 3 into 100 square less than or equal to this 300 by n square. So if you further write, then you will have this n square is equal to this 3 square by 3. So it means n is equal to root 3 is equal to 1.732. Okay, is it correct?
Yes, sir.
yes, sir.
Okay, so now let us go to the next one. That is 2015 session 1. So a machine element is subjected to following biaxial state of stress: sigma x is equal to 80, sigma y is equal to 20, tau xy is equal to 40 megapascal. If the shear strength of the material is 100 megapascal, the factor of safety as per Tresca's maximum shear stress theory is. Can you calculate this?
Yes.
So first you have to calculate that sigma 1, sigma 2, right, which is sigma x plus sigma y by 2 plus or minus under root of sigma x minus sigma y by 2 square
Sir, two.
plus tau xy square 2, huh? Okay,
Yeah.
because this sigma 1 2 will be giving you value of 100 and 0, right? If you put this sigma xy and tau xy in this equation, it will give you this 100 and 0. Everybody is getting this?
Yes.
Then tau xy is sigma 1 by 2, it means it is 50. So once you get this, then as per Tresca's maximum shear stress theory, this factor of safety is equal to maximum upon allowable, right? So this maximum upon allowable maximum is this one. So if you calculate, then you will have this 100 divided by 50, which is equal to 2. This is how you will get 2. Okay. So then next is this uniaxial yield stress of a material is 300 megapascal. According to von Mises criteria, the shear yield stress of the material, sorry,
173.
173.1. Why? Because tau y is equal to sigma y by root 3 as per this von Mises criterion. So sigma y is given as 300 by root 3 will be 173.1 megapascal. Okay. Okay.
Sir.
Okay. Then next is this one. Here what you have to do is, it is from GATE 2017 session 1. Consider the schematic of a riveted lap joint subjected to tensile load F as shown below. Let D be the diameter of rivets, SF be the maximum permissible tensile stress in the plates. What should be the minimum value of the thickness of the plates to guard against the tensile failure of the plates? Assume the plates to be identical. Can you calculate this? Hello? हेलो
ARR. जी सर.
ए आ रहा है. Okay, okay, correct. Why? Because here sigma maximum tensile can be equal to the force upon area, right? Force upon minimum area. So force upon minimum area will be along this particular line, right? As we have seen in that problem, W minus 2D into thickness. So F upon W minus 2D into thickness will be this maximum tensile stress, because here area is minimum in this plate. So then what is the maximum permissible tensile stress is SF. So it must be less than or equal to this maximum permissible stress. Then only the what we can say, this plate will not undergo failure, right? So F upon W minus 2D into T must be less than or equal to SF. So now what should be the minimum value of this thickness? So minimum value of thickness must be T must be greater than or equal to this F upon SF W minus 2T, right? So this is how it will be the answer. Okay, got it? Got it?
Sir.
Okay. So next is this: if sigma 1 and sigma 3 are algebraically largest and smallest principal stress, then the value of maximum shear stress is It is easy, right?
Yes, A.
B will be the answer, right? Sigma 1 minus sigma 3 by 2.
Sigma 1.
Okay. Now let us go to the next one. Here the bars of square and circular cross section with 0.5 meter length are made of a material with shear strength of 20 megapascal. The square bar cross section dimension is 4 cm by 4 cm and the cylindrical bar cross section diameter is 4 cm. The specimens are loaded as shown in the figure. Right, which specimen will fail due to applied load as per maximum shear stress theory? So can you calculate? You need to calculate stress in each the component, then you can check which is going to fail and which is not. Can you do that?
Yes, sir.
Please calculate.
Sir, would it be B?
It would be
Torsional. B.
anyone else?
सर वो बेंडिंग वाला है सी।
Anyone
Sir, क्यों
else?
सर torsional भी तो आ रहा है
See,
टेंसर
let us calculate one by one. So if we calculate for this tension and compression, then it will be same, right? That load upon area, that is load 80 into 10 raised to 3 upon area is 40 square, right? 4 centimeter is 40 mm. So Newton per mm square I have written, so it will be 50 Newton per mm square. Okay,
tau max would be 25 Newton per mm square, which is better.
Tau max is 50 by 2, that is 25 Newton per mm
Which is
square,
greater than 20.
which is greater than 20 MPa, right? So it is going to fail in both tension and compression, right? So actually only one option is there, right? So for torsion and bending it must
compressive भी होगा ना sir?
Yes, tension and compression both, no? So both it is written.
I thought
For
torsional.
yeah, for tau max it is what? Mt r by j, right? Correct? So if you calculate for this, it is coming around 16 megapascal, I guess.
थर्ड 15 आ रहा है,
right? And for bending moment it is mby upon I, right? So if you go for mby upon I, then you are finding, I guess, 50 the 30 megapascal, but as this is the tensile, your tau max will be 15. Tau max will be this, sorry, this is sigma, not b. This is sigma, right? This is tau and this is sigma. So this sigma is coming 30 megapascal, but when you go for this tau max, it will be sigma by 2, so it is 15 megapascal, so it is also less than 20 megapascal. Right here also less than 20 megapascal. Here mt is given as 64 pi, r will be d by 2, j will be pi by 32 d raised to 4, right? That's 64 pi into d by 2 and pi by 32 d raised to 4, like this, right?
Yes sir, yes sir.
Correct. So you will get that what we can say, tau max as 16 megapascal, right? That diameter is given, right? This cross section diameter is 4 centimeter. Okay. Hello.
हाँ सर.
ये वाला हो गया सर.
Okay, okay. And similarly here, actually as this is square, your this I will be that BD cube by 12, right? Like that you will get. Okay.
Yes.
It means that you okay, you will get it. So in short, you are getting these answers, right?
Yes.
Yes sir.
Okay. So this is how we are done with this design against static load, right?